I guess I'll just try to talk quietly. Can you guys hear me okay on Zoom? Okay, hi, I'm Liv. I'm a PhD student at the University of Melbourne. I want to thank the organizers for setting this up. It's really nice to be back here in Creswick. Last time I was here, I started this project, so it's nice to come back and speak on it. I also want to thank Dom for his lovely talk, because it's a nice little precursor to what I'm going to be getting into. The name of my talk is G-Monoidal infinity categories. As Dom spoke of, there are many models for infinity categories. I'm using the quasi-category model. And my hope for this talk is by the end, you will have an understanding of what a G-Monoidal infinity category should be and why the definition is what it is. But in order to get there, I'm going to do a bit of a precursor on just what monoidal categories are, what G-Monoidal 1 categories are, and then we can keep moving from there. So a monoidal category is an algebraic object in the category of categories. Specifically, it's going to be a category equipped with a functor of this form. And I'm going to switch dry erase markers to something a little fresher. We'll see how this one is. No, this one looks awful. No, that one looks bad too. Hold on a minute. This one seems okay. Okay, and then the idea is that the image of an ordered pair like A comma B is going to be the monoidal product, sometimes called the tensor product, and I'm going to denote it like A tensor B like this. Okay, so we would like for this monoidal product to be associative and unital, unsurprisingly, but we also want to be good category theorists. And so rather than having these things be associative and unital on the nose, we're going to do it up to isomorphism. So in other words, I'm going to have something like A tensor B. I'm switching markers again. Try a different color. Tensor, yeah, that looks better. A tensor B tensor C should be isomorphic to A tensor B tensor C. And similarly, we should have some sort of unit object, which I'm going to denote as 1 like this. And 1 tensor A should be isomorphic to A, should be isomorphic to A tensor 1. So the idea of a G-monoidal category is like, in the same sense that I have this weak associativity and unitality here, we want some notion of weak commutativity. So the most familiar example for most people of a G-monoidal category would be a symmetric monoidal category. So a symmetric monoidal category is a monoidal category that is all of these things so far, weakly unital, weakly associative, but it also is going to have natural isomorphisms relating A tensor B to B tensor A. And these are going to be natural in both variables. More specifically, and perhaps with a little example, if I have like, say, 4 objects in my category, which I'm going to denote like this, A1 tensor, A2 tensor, A3 tensor, A4, with some choice of order in which I'm multiplying these things. So perhaps I will denote this with parentheses. And then if I have, say, a different choice of parentheses, like this, just denoting a different order in which I'm multiplying these. And then I have this all being acted on by some symmetric group element that's just permuting the order of these objects, then there's going to be a unique isomorphism relating these two things. So the idea is we're going to want to sort of associate this isomorphism with this element of the symmetric group. So in this case, this sigma would be in the 4th symmetric group. Okay, so a G-monoidal category then is like a more general idea of this symmetric monoidal category. So a natural question one might ask themselves upon hearing the word G-monoidal is, what sort of object is G? The answer is it's something called an action operad, but I'm not going to go into too much detail about that. Instead, I'm going to say we're going to think of G as, let me just write over here. We're going to think of it as a sequence of groups indexed by the natural numbers, like this, a sequence of group homomorphisms, pi n from Gn to sigma n. And this does need to assemble into an operad. I'm not going to go into the details of that. That varies quite a bit from G to G also. But then a G-monoidal category is going to have a similar situation to here. But now, rather than having a unique isomorphism associated to this symmetric group element, I'm going to have an isomorphism here, G, for every G, such that in this case, pi 4 of G is equal to that symmetric group element. We call this the underlying permutation of our element G in this group. And yeah, so this should give you some good heuristic of what's happening with these G-monoidal categories, but I am going to write down the rigorous definition. Is it possible to move the camera to show me here? Perfect. So in order to write down a rigorous definition of the G-monoidal category, we're going to need to sort of take a little detour into the land of operads. And I promise I'll be somewhat gentle about this. So I'm going to first construct an operad called the parenthesized G operad. I'm going to denote it PAG like this. This is going to be an operad in the category of categories. So it's in cat, but at each level, each of my categories is going to be a groupoid, so only isomorphisms. So what do these groupoids look like? Well, let's look at PAG4 as an example. Its objects are going to be what's called parenthesized permutations. And they look something like this, maybe x3, x4, x2, x1, with some choice of parentheses. So maybe something like this. It should look somewhat familiar to this picture over here. Okay. Now my isomorphisms, because this is a groupoid between two objects, are going to look something like this. Maybe I have x4, x2 with this choice of parentheses, x1, x3. I'm going to have an isomorphism here, like this, and it's going to be associated to an element G, where once again, the idea is that I want pi 4 of G now to have an underlying permutation that sends 3, 4, 2, 1, 2, 4, 2, 1, 3, in this case, the fourth symmetric group. Okay, so this needs to assemble into an operad. Again, I'm not going to go into the details of the operatic composition, primarily because this varies from G to G. But if you're familiar with braid groups, one example might be in the case where my G is the braid groups. The operatic composition is going to come from a process called cabling. And the idea is that I have some braid. Where can I stand where there's the least feedback? I have some braid, and I'm going to replace a strand of this braid with an entire other braid. So if I have something wrapped around something, I'm not going to wrap an entire braid around that thing. And that gets out a notion of operatic composition. So the first thing we should note about, actually, this now allows us to get to the definition of a G-monoidal category. Okay, so definition. A G-monoidal 1 category, I'm going to call it A, is an algebra over the, oh my God, PAG operad. So if you're unfamiliar with algebras over operads, the idea is that A needs to be an object in the same category my operad is in. I said PAG is an operad in the category of categories. So far A is a category, which is at the very least what we need. And then further, it's going to come equipped with these structure maps, which look something like this. These need to satisfy quite a few things, including like symmetric equivariance and a notion of associativity. But I'm going to brush over that and instead kind of get to the nitty-gritty of it. Why does this give me what I want? So in the case of PAG2, there's an object called x1, x2. And if I look at its image, say with A, comma B, this is going to define my monodal product. This is going to be a map from A2 to A associated to this object. So this is going to map down to, or this is going to be equal to A tensor B. Now, if I do the same sort of thing here, gamma 2 of now x2, x1, where I've swapped these things, this is an object in PAG2, with the same objects of A, this is going to give me a sort of swap monodal product map. And now if I have an isomorphism between these things in my PAG operad, or in this case, PAG2 groupoid, like this, I'm going to get out one of these commutativity isomorphisms that I seek. So this definition, what we should note about it is that it recovers our normal definition of symmetric monodal category. It recovers our normal definition of braided monodal category. It allows us to define some new notions such as like ribbon braided monodal, as well as if you construct a parenthesized G operad, where G is the action operad built from something called cactus groups, we can get out something called a cactus monodal category. And it turns out that the definition of a cactus monodal category is the same as the definition of something called a co-boundary category. And co-boundary categories show up in the representation theory of quantum groups. Okay, great. So now that we have like some understanding of what a G-monodal 1 category is, we have a definition down for it, we can start moving towards understanding the infinity context. So, yes.
You normally have those maps on the being subjective?
No, it's not necessary.
Are there any natural examples where they are subjective?
No. I think all the like heavy hitters are subjective, but it is not part of the definition. You can construct ones. In fact, no, there's an obvious one, monoidal categories. You pick the trivial action operad. Yeah. Okay, great. So in order to get to a point where we can understand the definition of a G-monodal infinity category, I'm going to first go over the definition of something that already existed in the literature, a symmetric monodal infinity category. So I'm going to write down this definition. It's going to sound like a bunch of nonsense words to most of us. And then we're going to sort of parse through it and try to understand why this definition is what it is. So a symmetric monoidal infinity category is a co-Cartesian fibration over the nerve of the category of finite finite sets. So it'll look something like this. I have some simplicial set CO times. I'm going to switch markers again. How's this one work? Not great. Just not having any luck with these markers.
There's a million there, though.
I know, right? Okay, let's try this one. And then this is, no, wow. This is going to go down to the nerve of finite pointed sets. So if I really wanted to, I could have an entire talk just on what a co-Cartesian fibration is. And I don't want to do that particularly. And so we're going to cheat a little bit. We're going to cheat a little bit. We're going to cheat a little bit. And I'm going to use an equivalence that's given to us by the infinity one Burton deconstruction. Okay. So the infinity one Groton deconstruction is going to give us an equivalence between, oh, you know what? I didn't finish this definition. It's more than just a co-Cartesian fibration over the nerve of finite pointed sets. It also needs to satisfy, a Siegel condition. How is that worse? Okay. And the Siegel condition says that the fiber over one, if I take like the nth Cartesian product of this, it should be isomorphic to the fiber over m. And specifically, this needs to be induced by specific morphisms in the category of finite pointed sets, but I'm not going to go into too much detail. Okay, back to infinity one Groton deconstruction land. This gives us an equivalence that tells me co-Cartesian fibrations of this form are going to be equivalent to infinity functors, which you can just think of as maps of simplicial sets from the nerve of finite pointed sets into the infinity category of infinity categories. And further, because this satisfied this Siegel condition, this will also satisfy a sort of Siegel condition where if I denote the image of one as C1 like this, and the image of n as Cn like this, then once again, this needs to be isomorphic this way. Okay, so why is this the right definition for a symmetric monodal infinity category? Well, in order to make sense of that, what we're going to do is we're going to look at a fairly specific two simplex that exists in the nerve of finite pointed sets. And this two simplex is going to look like this. We're going to have a map from 2 to 2 down to 1. And this is filled in. This first map here is going to be a sort of swap map. And these are going to be a sort of monoidal product map. And what I mean by that is this first map sigma is going to look something like this, where I'm just swapping 1 and 2. This is a map of finite pointed sets. The second map, so this is sigma. The second map is from 2 to 1. It's going to look something like this, where I just send 1 and 2 both to 1. Now, if you notice, if I compose these things, this composition is still just a map that sends 1 to 1 and 2 to 1. So they compose to be the same thing, which means that in its nerve over here, I'm going to have some sort of filling thing here. Okay, so we're going to look at the image of this under a functor like this. All right. So the image of this thing is going to look something like C2 to C2 to C1. This is going to be filled in by something. Now C2, as I mentioned before, is going to be isomorphic to C1 squared. Okay, this map is going to be a sort of swap map where I'm just permuting my objects. This is going to be how I define my monodal product. And this is going to represent our sort of natural isomorphism, giving us our commutativity that we want. Okay. So with that done, we can start building towards the definition of G-monodal infinity. But in order to do that, we need to first sort of replace what the category or what the nerve of the category of finite pointed sets did here with some other construction. Okay. So we're going to start by building something I call GPD. This is a category enriched in groupoids. Its objects are going to be finite ordinals, so 1, 2, n, and so forth. And its Hom groupoids are going to look something like this. I'm going to take a coproduct over maps F from N to M in the category of finite pointed sets over a product indexed 1 less than or equal to I less than or equal to M. And then here I'm going to write some words and then explain them. Okay. So what this is I can construct, I described this operad PAG earlier. I can construct a similar operad where everything is the same except for now the objects no longer have parentheses. And then this is going to be one of those groupoids. And the number, like the level, the arity that I'm grabbing this groupoid from is going to come from the cardinality of the pre-image of I. So like as an example, if I have as my underlying map of finite pointed sets, 1, 2, 3 here, going down to 1, 2, say 1 goes to 2, but 2 and 3 both go to 1. And what I'm going to need here is an element of op G2 corresponding to the cardinality of the preimage of 1, and I'm going to need an element in op G1 corresponding to the cardinality of the preimage of 2. What?
Figure writing.
Figure writing. Okay, yeah, sorry. So great. So how does composition work in this category? It's actually going to be inherited entirely from the category of finite pointed sets and the operatic composition of my operad op G. Okay, so now that I have a category enriched in groupoids, I'm going to do some stuff to it. The first thing I'm going to do is I'm going to take the nerve of each of my Hom groupoids, and that'll give me out a simplicial category. So I take the nerve of each of these things, I get out a simplicial category, I call it G space. One important thing to note about this is that each of my Hom groupoids is a groupoid, and so each of its nerves is going to be a Kohn complex. So in particular, this is going to be a fibrant simplicial category. Further, because each of my elements in the Hom groupoid has an underlying map of finite pointed sets, this comes equipped with a sort of forgetful functor to the category of finite pointed sets, thought of as now a discrete simplicial category. And there's a theorem in higher algebra that tells me that when I have this exact situation where this is fibrant, that if I take the nerve of this, I get out what's called an infinity operad. And by nerve, I mean here simplicial nerve or homotopy coherent nerve, some people call it. I'm not going to go into detail of what an infinity operad is. For now, we're just going to be like, ooh, ah, that's amazing. We have what we want. And I'm going to call this now GO times. Okay. So now I can finally get to my definition.
Running low on time. Yeah.
Okay, I will be quick. I'm going to have to brush over theorems at the end and just like briefly describe them. But anyways, definition. A G-Monoidal infinity category is a co-Cartesian fibration over GO times. So something that looks like this. We're once again going to use that infinity one group deconstruction to sort of parse why this is the right definition. So this is going to be equivalent to an infinity functor that looks something like this. Before, when we were trying to make sense of the definition of a symmetric monodal infinity category, we looked at the image of a two simplex. I'm going to do the same thing here, but this one's going to be a little different. Okay. This first one simplex is going to come from one of my morphisms in G groupoid. So it's going to have an underlying map of finite pointed sets. I'm going to choose a bijective one. So a bijective map of finite sets is just a permutation. We're going to think of this as a permutation. I then need to pick n choices of objects in the first op G, so op G1. I'm going to pick the unit ones. We're just going to call this sigma and move on with our lives. For this one, I'm going to choose as my map, underlying map of finite pointed sets, the map that sends 1 through n all to 1. We're going to think of this as our monodal product. And then I need a single object because there's only one thing to look at the preimage of. I'm going to choose the object that looks like this. Remember, no parentheses in this one. I'm going to do the same thing here. Great. And because of the way the homotopy coherent nerve works, I'm going to have two cells here filling this with a G such that pi n of G is sigma. So if we look at the image of this under my functor, I'm going to get something that looks like this. Where this is now we're going to think of as our sort of swap map, where it's just permuting the different objects of these things, because once again, this is going to be isomorphic to V1 to the n. And this is going to be thought of as our monodal product. And so this two cell here is now giving us our natural isomorphisms. They're going to be associated to all of the elements G, that's underlying permutation is sigma, and we get out exactly what we want. Okay, just as my very last thing, I'm going to quickly write down 3 theorems that will convince you this is the right definition. The first one, and these are all 9. A symmetric monodal infinity category is equivalent to a G-monoidal infinity category where G is the symmetric groups. This is still true if I replace symmetric with braided and I replace sigma with the braid groups. This is still true if I replace symmetric with the empty set as in monoidal and choose the trivial G operand here. Okay, and then the last thing is a sort of nerve theorem, which I have one direction for, I'm working on the other one. And it says that if a 1 category C has a G-monoidal structure, then the nerve of C has a G-monoidal infinity structure. And that is all. Thank you so much.
All right. All right, do we have any questions? Yeah.
Yes, one, three.
All right. So could you give like an explicit definition in the case of a trivial group of like the end thing that you get? Like for just a monoidal with no symmetry infinity category?
I'm a little confused by your question. Jacob Lurie has a definition for a monoidal infinity category. It's based off of, he builds an infinity operad that he calls a SOS. And then he has a definition of an O-monoidal infinity category. My definition, where I choose the trivial action operad, I get out an infinity operad that is equivalent to a SOS. And then my definition is the same thing. I've just written it differently as a co-Cartesian fibration. So yeah, you get out the same sort of structure. Does that help?
But I guess like in the finite set case, I can sort of see why a functor from nerve of finite pointed sets looks like symmetric monoidal category. But like, I guess how would you do a monoidal structure? Like, is there an easy description of the main category to see that you get a monoidal structure without